Thank you so much for the introduction. Hello, everybody. My name is Pantea Karimi. I'm a PhD student at MIT and a student researcher at Microsoft Research. And today I have the pleasure of introducing MetaEase, the first heuristic analyzer from source code. In large-scale systems, we constantly face optimization problems that are slow or even intractable to run at scale. So what do? We come up with approximate solutions or heuristics. Examples of real deployed heuristics are demand pinning in traffic engineering, first bit decreasing in VM placement, LLQ in load balancing, and so on. These heuristics work well most of the time, but because we're choosing to run an approximate solution instead of an optimal one, we're at the risk of underperformance and inefficiency. That means for large-scale systems, there would be degraded user experience and wasted resources. This problem has always existed. But because we're increasingly using coding agents into our production codes, now a lot of heuristics are generated with minimal human insight about their failure modes. So we need good automated tools to analyze heuristics. Let me give you an example. In traffic engineering, the inputs, denoted by I, are traffic matrices. The performance objective is to maximize the routed traffic on a network. The optimal solution is slow at scale. We show optimal performance on input I with opt of I. In practice, people run heuristics. A heuristic that was previously used in Azure is called demand pinning. It has a simple logic. For demands that are smaller than a threshold, it pins them to their shortest path. Otherwise, it routes them optimally. We show its performance on input I with heuristic of I. We call the difference between the heuristic and optimal performance gap. Prior work shows that demand pinning may have a 30% performance gap on some topologies. That means that Azure had to tolerate 30% performance gap on some of its inputs, which is a lot. Consequently, we're interested in systematically analyzing the worst-case scenarios of a heuristic. Visually, you can think of this gap as a landscape over the input space, where the valleys are where heuristics are performing fine compared to the optimal, but the peaks are where the heuristic is underperforming. We're interested in finding these peaks, the failure scenarios where the developers should be aware of before they deploy the heuristic in production. There are some existing tools for heuristic analysis. For example, our community developed Explain, MetaOp, and FPerf. These are very powerful tools, but they all require you to encode your arbitrary heuristic into a mathematical format. For example, optimization or SAT. To give you an example, if you were to use MetaOp, you would have to encode the demand pinning heuristic into an optimization formulation. This is actually a difficult thing to do, and you need to have domain expertise about optimization, bi-level optimization, binary variables, and so on. So these tools are generally hard to use or domain specific. To make things worse, if you have a new heuristic that you want to analyze, you need to re-encode everything from scratch. We introduce MetaEase. In MetaEase, you just bring your heuristic code. There is no encoding or mathematical formulation needed. The same heuristic you use in the production, you can analyze it. This is a much simpler interface for developers. Along with the code, the developer should provide basically the optimal formulation, the thing they want to compare the heuristic against, which is usually a fixed and well-known optimization. There are two key challenges in doing heuristic analysis from source code. First, that gap sampling is expensive, and second, we want to avoid the local maxima. Let me explain them in detail. First, the gap is opt of I minus heuristic of I. We don't have any analytical formulation of the gap. We just have its code. So if we were to measure the gap on an input, we have to run the heuristic code, run the optimal, and subtract the values. The optimal is an expensive function to run. That's why we have a heuristic for it. So gap sampling is expensive. And naive approaches that rely on a lot of gap sampling are pretty inefficient. So how can we make progress efficiently without a lot of gap sampling? The second challenge is the gap function can be pretty non-smooth with a lot of local maximas. How can we find a true global maxima? In MetaHe's, we have mechanisms to address both of these challenges. Instead of repeatedly sampling the gap, we use a modified gradient ascent process. And to avoid getting stuck in local optima, we use symbolic execution to generate smart seeds based on the heuristic code. Now let's dive deep into MetaHe's design. Remember, we want to maximize the gap, opt of I minus heuristic of I. Instead of computing the gap, if we take the gradient of the gap, we would have gradient of opt minus gradient of heuristic. Here's the insight. Although computing the gap function is expensive, computing its gradient is actually cheap. So what we do in Meta is we separately estimate the gradient of optimal and heuristic. We subtract them and we use it as our guiding direction. For the gradient of the optimal, we approximate it without repeatedly sampling the optimal. We use duality theory to do it, and the mathematical details of this approach are in the paper. But to give you an intuition, if you're at some point in the input space, you can estimate the direction of the optimal and take a few steps toward it. But if you want to know the actual value of the optimal, you have to take many, many more steps to converge to the value of the optimal. OK, now that we have a way to approximate the gradient of optimal, how do we approximate the gradient of the heuristic? The heuristic is an arbitrary piece of code. We don't have any analytical formulation to differentiate. Our idea is to use Gaussian process to estimate the gradient of heuristic locally. Gaussian process is a smooth differentiable function that can approximate any function given enough local samples. So let me show you how it works. Here's our input space. We have two dimensions, let's say x1 and x2. We are at some point I, and we want to measure the heuristic gradient at this point. We sample locally around I in a block. We run heuristic code on these samples, and we fit a Gaussian process on these samples. Then we use the analytical formulation of the gradient of Gaussian process to estimate the gradient of heuristic with the gradient of Gaussian process. This is a sample efficient and fast way to approximate the gradient of heuristic. Now let's see the full gradient ascent in motion in MetaHe's. We start at some point, let's say I0. In a local neighborhood around it, we sample heuristic. We feed a Gaussian process. We estimate the gradient of heuristic. Separately, we estimate the gradient of optimal. We subtract to get the gradient of the gap, and we move to, in that direction. We get the next point I1. We repeat the same thing: sample, refeed, estimate, and subtract, and move. This way, I showed you 3 iterations of how we move in the gap space without computing the gap function. All right, now that we know how MetaHe's gradient ascent work, let's see what it does to avoid the local maximas. So far, we have an efficient gradient ascent mechanism that can start from a point and follow a trajectory in the gap space. Now, where do we start this from? If we pick random sampling, a lot of the times we might get stuck in local optima. So we need a principled way to choose the seed to make sure that we land in different regions of the landscape. We want seeds that fundamentally trigger different, that they cover different regions of this landscape. If there was a way that we could partition the input space into these different regions, where within one region the heuristic has the same behavior, but it behaves differently across the regions, then that would have been really nice. In formal verification, we call these partitions equivalence classes. In MetaHe's, we take one seed from each of these equivalence classes, and consequently, we exploit all the different behaviors of the heuristic. We believe that heuristic code paths are good equivalence classes. Let me show you. Remember, in the demand pinning, we had an if-else branch based on the value of the demand compared to a threshold. This effectively splits the input space into multiple code paths. So for two demands, I1 and I2, we have 4 different code paths where both of them pinned, only I1 or I2 is pinned, or none of them are pinned. If we actually look at the gap values across these different regions, we see that the gap function is smooth in the code paths, but there are cliffs between the different code paths. So if we randomly sample points in this space and we do our gradient ascent on it, we might miss the worst case code path and not get to the worst case possible value. In MetaEase, we run symbolic execution on the code to get representative seeds for all the code paths. That way, we would have made sure that we have exploited all the different code paths. And we find the worst case possible scenario in all the code paths. So in MetaEase, we run symbolic execution, and in our implementation, we use CLE to find the seeds. Now, what about the non-differentiable cliffs between the code paths? We assume within each code path, the heuristic relatively has a good behavior. So we restrict the search within a code path. And if the gradient step is moving toward outside the code path, we project it back to the code path by moving to the most aligned point with the gradient. That way, we make sure that we're only exploring that code path. Putting it all together, if the heuristic developer takes the heuristic code and optimal formulation, based on the heuristic code, we run symbolic execution and generate seeds. And for each seed, we run MetaEase's modified gradient ascent. Now, let me show you some results. We compared MetaEase with MetaUp, which is the state-of-the-art heuristic analyzer. If you were to use MetaEase, you would provide your heuristic demand pinning production code. But if you wanted to use MetaUp, you would have to encode it as optimization. Now, in the same time budget, I'm going to show you the gap ratio, which is the maximum gap found by MetaEase divided by the maximum gap found by MetaUp. So values more than 100% means that MetaEase found a larger gap in the same time budget. On demand pinning across 5 topologies, we found a gap larger than 90%, and for larger topologies, we found a higher gap. The same trend holds across the different domains that we tried. We also compared MetaEase with black box approaches. The x-axis is time, the y-axis is the best gap found so far. For demand pinning on abelian topology, we found MetaEase consistently finds larger gap compared to black box approaches. The same trend holds across different topology and other domains. MetaEase can analyze a heuristic as long as it takes an input and it outputs a performance metric. We analyzed DOTE, which is a DNN-based traffic engineering heuristic. And compared to a specialized DNN analyzer from Hotness 2024, we found a larger gap. We also analyzed Arrow, which is a heuristic for optical IP traffic engineering. Arrow is a randomized heuristic with non-convex behavior. Compared to all the black box approaches, we found larger gap. I want to highlight that MetaEase can analyze these heuristics while most of the other analyzers either can't analyze them or they have a very hard time. They need a really hard encoding. It's because MetaEase doesn't care about the structure of the heuristic. It just runs its code. In conclusion, MetaEase is the first general domain heuristic analyzer that works from the source code. It's open source, and it's available in the QR code above. It matches or beats the state-of-the-art across multiple domains and heuristic. And I want you to think about MetaEase not only as a heuristic analyzer, but as a tool for you to develop better heuristics, where it sits in a continuous improvement loop, and it takes new heuristics. And after you run it and get these worst-case scenarios, you can do root cause analysis, safe deployment, and regression testing. Thank you so much, and I would love to answer your questions now.